Hello everyone and welcome back. In this video I'm going to go over the nature of energy. I'm going to define a few things. I did this in an earlier video, but it's always good to review, and I'm going to tie this into what we're going to be talking about in later videos with regard to thermodynamics. So just to recap or review some definitions. Energy is defined as the capacity to do work. So if we understand the capacity to do work, it's the ability the ability to do work. If you don't have the capacity to do work, or if you don't have energy, then you're not going to be able to do anything. So we kind of understand this in a kind of normal, everyday sense of the word, right? So if I come home tired, I lack energy. I just want to go. I just want to go home, sleep, rest, whatever. I don't want to do anything because I don't have energy. So I don't want to work. But in this case, work has a more of a technical definition. So work here means it's the result of a force that's applied through a distance, right? So I don't actually do work unless I'm pushing something, right? Or pulling something, because that's what a force is. Any push or pull is a force. So if I'm going to push up against this wall, the wall doesn't move. So I am not doing any work on the wall, but I will expend energy in the form of heat and things like that, because I'm trying to push the wall. My body temperature goes up. My muscles are tensing, so I am using up energy in a sense that way. But I'm not. The force that I'm pushing on the wall is not really moving anything, so there's no work being done. So that's what we mean by work. um, so here I have a little diagram to kind of see where energy fits in and how it's divided. And so energy is divided into two main groups. You have kinetic energy and you have potential energy. Kinetic energy is due to motion, so it's the energy of motion. So anytime something is moving, it's going to have motion. It's going to have kinetic energy. So energy due to motion. And so here is the equation for kinetic energy. It's kinetic energy is equal to 1 half mv squared. We saw that earlier in the chapter when we're dealing with gases. Okay, so the motion of particles. We also have a subset of kinetic energy, which is called thermal energy. It's also referred to as internal kinetic energy. And the reason it's called internal kinetic energy is because it's referring to the particles that make up the object. So the particles themselves are going to have motion. So there's a kinetic energy there, but we call that thermal kinetic energy because it's related to temperature. So the temperature of the object is a measurement of that internal kinetic energy, the motion of the particles. Okay, so it's a type of kinetic energy. So we'll be talking about thermal energy a lot. Also, one thing we'll be talking about is potential energy. So potential energy can be potential energy with respect to position or with respect to composition. So when we're thinking about an example of if I hold my phone at a certain distance above the ground, then it has a certain potential energy with respect to the ground. If I drop my phone, no, I'm not going to drop my phone. So if I drop my phone, it's going to fall. That potential energy is going to become kinetic energy, right? So, but as it's falling, it's going to lose potential energy, and that potential energy that's lost is going to be picked up by kinetic energy as it speeds up. So that would be what we call gravitational potential energy, because it's related to gravity acting on the object. The one that we are more interested in is the energy due to composition, potential energy due to composition. And that's going to be related to what we are going to call chemical potential energy, or just chemical energy, which is going to be related to the positions of nuclei and electrons, right? So the nuclei of atoms are positive and the electrons are negative. So how the electrons are positioned in an atom or between two atoms, right, that are bonded together, right? So if the electrons are between the two positive the two positive nuclei, then the positive nuclei are going to be attracted to the electrons. The electrons are going to be attracted to the positive nuclei, and so, but then the positive nuclei are not going to be attracted to each other. So there's this balancing act between being uh, attracted to the electrons, but also being repelled from the positive. So it's going to meet a balance, and that's what we call chemical bonds, right? So it's attractive force, and so that's going to be potential energy. It's a kinetic potential. It's a chemical potential energy. Okay, the next thing I want to talk about is go back to the law of conservation of energy. So we talked about this in chapter 1. So all of this is review so far. So in chapter 1, we talked about the conservation of energy, that energy is neither created nor destroyed, it's only transferred in form, from one form to the other. And so this is represented by this equation here, that the energy of the universe, the total energy of the universe, is going to be equal to the energy of a system plus the energy of the surroundings. Now, what do I mean by energy of system and surroundings? Well, the energy of a system is whatever you choose it to be, whatever your focus is on, right? So in chemistry, our focus is going to be on reactions, and maybe the container that the reactions are happening in. But they're mainly going to be the reaction. So what's going on with the reaction? That's our system, right? Does the system lose energy? Does it gain energy? That's when we're going to be talking about, exothermic reactions versus endothermic reactions, right? So does it lose heat? Does it gain heat? Does it lose energy? Does it gain energy, right? So that's going to be our system, the reaction. Everything else that is outside of the reaction is going to be considered surroundings, right? And that means everything, right? So if my reaction is happening in this little beaker here, then everything outside it, the universe, the moon, the stars, the galaxies out there, that's all considered the surroundings. And the universe is considered those two together, right? So my little system that I'm kind of cutting out from the rest of the universe, that is my system. And then everything else that is not the system is the surroundings. And those two together make up the universe, right? So that's what the equation is referring to. And finally, the last thing I want to talk about is units. We talked about energy units before. So if we go back to the equation, kinetic energy equals 1/2 mv squared. You remember that mass times velocity squared, that's going to be kilograms multiplied by meters squared over seconds squared. So this comes directly from the kinetic energy equation. So since kinetic energy is energy, these are the units, or this is the derived unit of energy. And so 1 kilogram meters squared per second squared, that is equal to 1 joule. So these are equal to each other. So one of these is equal to one of these. The other unit that you want to be familiar with is the calorie, small c calorie. Now, it used to be defined when I was growing up, it was defined as the amount of energy needed to raise 1 gram of water by 1 gram by 1 degree Celsius. So they don't define it that way anymore. It's now defined as 1 calorie is equal to 4.184 joules, and this is exact. This is not a measure. So when you use this as a conversion factor, then you don't have to worry about the fact that this has 4 digits, right? Because it's exact, it's going to be an infinite number of digits, so you don't have to worry about that when you use it to multiply or convert. Okay, that's it that I wanted to cover in this video. In the next video, we will go over more about energy and the system and surroundings relationship. Thank you for joining me. If you like this video, like it, share the video with your friends, subscribe to the channel, and make a comment in the comment section and let me know what you think, and if you have any questions or any videos you want me to do. Thanks for joining me, and I'll see you next time.